Okay, so there was one question left. I actually forgot to discuss in the last class. This is the last question Siddharth was asking. What is d2x and d2y? These are double differentiation with respect to x and double differentiation with respect to y. So I'll discuss what is d2x. You can also find out what is d2y. So d2x is del square by del x square of iz at n plus 1 time instant. We're actually doing double differentiation of iz with respect to x at the n plus 1 time instant. This was actually the notation for d2x. Had it been d2y, then x would be replaced by y here. So del square by del y square. So if you know what is del square by del x square, you can also do del square by del y square for the iz at n plus 1 time instant. And the location, this is a 2D case, so we have only I and j as running index. I plus half, j plus half here. So this is the location here. So let us just do the first differentiation del by del x of this iz at n plus 1. First differentiation is with respect to x. So what is the running index for x? I is the running index for x. So iz at n plus 1, iz at n plus 1, running index for I will be I plus 1 here, I here. So we are doing partial derivative with respect to x. So I plus 1, I divided by delta x. J is still the same, j plus half here. Then you again do the differentiation of this one, double differentiation, no? Del by del x of this whole term here. So you do the differentiation of this first term and second term here. First term, when you differentiate it, what do you get? So iz at the same time instant, but now space location is changed because we are doing again differentiation with respect to x. So I plus 3 by 2 minus I plus half here. So again, you do the differentiation of this will become I plus half, I minus half. You combine all this term, there are 4 terms here. This term and this term, if you look at it, they're same. So you write here 2iz n plus 1 I plus half j plus half. This is the second term. First term and last term still remains the same. And because of the double differentiation, you have a delta x square here. So you can easily do it for d2y also. So let us come back to that was the digression because you had a lot of questions on the this advanced Fdtd. So let us come back to the Fdtd model for the dispersive materials, and you know what is dispersive material now, frequency dispersive materials. So now in the frequency domain equation for Debye model, this is what we have derived. From there we have done the digression. So these are the equation we have derived, and yeah, this is the equation we have derived. So 1 plus j omega tau naught d equal to epsilon 0 epsilon infinity j omega tau naught epsilon 0 epsilon dc e here. So d is the this is what we call it auxiliary field. No? E is the electric field, and this is a relation between D and E. And if you want to write the update equation for this, all I need to do is replace this j omega term by time derivative, because time harmonic fields, when you do the differentiation with respect to time, you get j omega. So del by del t of this d plus tau naught j omega will be replaced by del t when I take inverse Fourier transform equal to epsilon 0 epsilon dc electric field. Now we are in time domain, so this bar here is showing that we are in time domain. Previously it was in the frequency domain. Then you have tau naught epsilon 0 epsilon infinity j omega would be replaced by del t electric field in the time domain. So this is the equation we want to do the discretization. You can do it, discretization, you can easily do it. You can just replace this del by del t here, and you can rearrange the term. If I want to find En plus 1, then I need to find what is Dn plus 1, Dn and En. So Dn and En are of the previous time instant value of D and E, but we do not know what is the Dn plus 1 because this is at the same time instant. So how do I find this Dn plus 1? If I know Dn plus 1, Dn and En, I can find out what is En plus 1. So I need to know what is Dn plus 1. So if I want to know what is Dn plus 1, I need to have this equation here. This is one of the Maxwell equations. And if we assume that there is no dispersion in the magnetic permeability, that means magnetic permeability mu here is independent of frequency. Usually, if you consider dielectric material, mu is not going to change. Mu is equal to mu naught. So there is no dispersion for the magnetic permeability. In that case, this is one of the Maxwell equation. You can easily do the update equation for this. If you want to find Hn plus half, you can find it from the Hn minus half and this equation at the nth time instant. So you can separate it out, but we have written it in a very compact form now because we are almost at the end of the Fdtd. You know how to do this. So if I want to find Hn plus half, I need Hn minus half and electric field at nth time instant. So I can find out Hn plus half. Because why I'm finding out this Hn plus half is because when I want to find Dn plus 1, I need to know what is Hn plus half. That will be very clear from this next equation. This again another Maxwell equations, Maxwell curl equations. So the del by del T of D equal to curl of H. So I wanted to find Dn plus 1. So I can find it out from here. Dn plus 1 is equal to Dn minus delta T curl of H at n plus half. So I already know what is n I equation. So I can find out Hn plus half from here. I can substitute it here, then I can find out what is Dn plus 1. So once I have this Dn plus 1, I know what is Dn, En, I know Dn plus 1, I can find out what is En plus 1. That's the procedures. We want to write the update equation for electric field. Once I know what is the update equation with Dn plus 1, I know what is the value of Dn and En of the previous time instant, I can find out what is En plus 1. Okay, so that is for the case when I assume that there is one single pole, dipole. So this is the dipole model we are considering. In the dipole model, you can have many poles. You can have many poles. So as I already told you in the last class, you consider many poles and do curve fitting. And if you get a proper model, then you can say that this material is behaving like a dipole model. So it's curve fitting, and you can assume many poles. And usually in medium also you can have many poles because let's say you have a bounded electron to the nucleus. When you supply the external electric field, all the bounded electrons, many of them will almost start oscillating. You displace it, then it will again come back. If it is not bounded, it will keep on moving. If it is bounded, then it will come back to the original state. So from there you can have multiple resonance inside the medium. So in that case, instead of just having this delta epsilon by 1 plus j omega tau naught, we'll have many of them, many dipoles. Because of that, your complex electric field will be contribution from the free space epsilon 0, epsilon infinity. Usually epsilon infinity for practical material is 1. But when you do Fdtd simulation, you can assume anything. That's why we have put it epsilon 0 into epsilon infinity. This is the contribution from the free space, and this is the contribution from the polarization of the medium. So here, because of having multiple dipoles, we'll have many of them. So you can sum them up, summation m going from 1 to capital M. So delta epsilon m divided by 1 plus j omega tau naught m. So delta epsilon m is the difference between the epsilon at DC and epsilon at infinity for the resonance we are considering. We are assuming many of them. So how do I write the update equation for the polarization current? Polarization current we can denote is as Jp. Jp is varying with respect to time. If you do partial derivative with respect to time of the polarization field, you get polarization current. So Jp is basically del P by del T. So now for the dipole material, we have considered epsilon, complex epsilon is just epsilon 0, epsilon infinity plus epsilon 0 delta epsilon m divided by j omega 1 plus j omega tau naught m. That was what we have just discussed in the previous slide. So from there, I want to write the update equation for the polarization field and polarization current. So this is the relation you have here. So what is the relation between the electric field and the polarization current? So if you just multiply by the electric permittivity with the electric field, you get the polarization field. So polarization field, if you differentiate it, you get the polarization current. So this is what you have. So j omega jpm is equal to this. So jpm is equal to this relation you have here. So from there you can find out what is the update equation for Jp. Jp is the polarization current. So why do we need to have the update equation for polarization current is because in the Maxwell equation, curl of H is equal to this is displacement current and this is a polarization current. So we have contribution both from the displacement current and polarization current because we are applying some external field to the medium. So we'll also have some polarization field. Because of that, we'll have polarization current. So this is for multiple dipoles. So we'll have M of them. So M going from 1 to capital M. This is JP1, JP2 up to JPM. So we have multiple dipoles. Because of that, we'll have multiple polarization currents. So this is the summation of all of them. So curl of H is equal to conduction, this is the correction displacement current and this is the polarization current. So you can write the update equation from here. So before that, let us try to write the update equation for the JPM because this is required here. No? So JPM is you have the relation just derived now in the previous slide. JPM plus J omega tau naught JPM is equal to J omega epsilon 0 delta epsilon E here. So now if I want to write the update equation, everything should be in time domain. So all the J omega tau would be replaced by del T. So JPM plus tau 0 M del T of JPM is equal to epsilon 0 delta epsilon M. See, this J omega will be replaced by del T of electric field. So you can easily write the update equation from here. JPM n plus 1 is equal to this term into JPM at nth time instant plus this term. And what is this? En plus 1 minus En by delta T. So from here you can write the update equation for JPM at n plus 1 time instant. Okay, so if I want to find JPM at n plus half, I can usually find out from JPM at n plus 1 plus JPM at n divided by 2. So this is the relation you have here. So now let us come back to the original equation. Original equation is here. This is the Maxwell curl equation. So you can write the update equation now. Left hand side, you're calculating magnetic field at n plus half time instant. Then right hand side, you have this epsilon 0 epsilon infinity. What was here? This is the displacement current. So del T, del E by del T. So En plus 1 minus En divided by delta T. And what is this? This is the polarization current. We calculate this at n plus half time instant. And it is actually a brace of the JPM at n plus 1 and JPM at n. You know what is JPM at n? This is the value of the previous time instant. You can find out JPM at n plus 1 from the previous slide. So you can find out what is this JPM at n plus half time instant. So from there you can write the update equation. So finally the update equation, this should actually be JPM here, no, it should not be PPM. So En plus 1 is equal to En, then this term here, curl of H n plus half minus half divided by summation going from 1 to capital M 1 plus Km JPM at n. So you know what is JPM at n, you know what is H at n plus half, you know what is En, then you can find out what is En plus 1. And this constant here, you call this as Km, and this constant here, you call it beta M. So in the expression for this En plus 1, you have this summation M going from 1 to capital M beta M. Beta M is this term here, and Km is this term here. Km is also existing here. So finally, if you have En, Pn, and Hn plus half, En you can find out from, once you have En, Pn, and Hn plus half, you can find out En plus 1. So En plus 1 is En, this term here, then Hn plus half, then you have JPM at n. So once you have JPM at n, then H at n plus half En, then you can find out En plus 1. And Pn and JPM are related. You take the derivative of Pn, you get the JPM. How do you get it? So Jp is equal to del P by del T. So from here you can do the update equation. JPM is, you can do update equation from here. So we have already discussed all of them before. So I can find out En plus 1. Once I have En plus 1, I can also find out Pn plus 1 from this relation. And one more thing is that I can also find out what is H at n plus 3 by 2 from this relation here. So del H by del T is equal to minus 1 by mu. Curl of it is a Maxwell curl equation. From here you can find out Hn plus half is equal to Hn minus half delta T by mu curl of E at nth time instant. So here, if you can replace this n plus half by n plus 3 by 2, you can find out from here. So once you have that, you can also find out E from here, from this relation. So that's how you do it. Let's go back to the another material, which is more generalized material, which is called Lorentz material. Lorentz materials are widely used for modeling any kind of materials. It can model especially dielectrics. Drude can model metals, and if you combine Lorentz and Drude or Lorentz and Debye, you can model any kind of material, including dielectrics and metals. So in the Lorentz model, you know that the electric substitutability for Lorentz model is L divided by minus omega squared j gamma L omega plus omega naught square. But you can write this whole term in terms of the delta epsilon m, that you can derive it equal to epsilon dc at m. Like we have done for the Debye model, you can do it for the Lorentz model also. Delta epsilon m is the difference of the epsilon at dc and epsilon at infinity. Epsilon at dc is at the frequency equal to 0. Epsilon at infinity is at frequency tending to infinity. Usually for practical material, this turns out to be 1. But if you have artificial medium, you can assume this as any value. So we'll just retain epsilon infinity here, but practical material, this will be 1. So epsilon for Lorentz, you can derive it similar to what you have done for Debye model. It turns out to be epsilon times inside the bracket epsilon infinity plus delta epsilon omega naught square divided by minus omega square plus 2j omega delta plus omega naught square. Delta epsilon is defined here. Delta you can find out from here. So this is the epsilon for the Lorentz case, and from there you can find out the update equation. If you have multiple poles, pairs, so basically instead of having only one single pole pair, if you have m multiple pole pairs, the second term here will be summation going from m going from 1 to capital N. Since you have omega square here, this will have multiple poles. This will have pole pair. No? Omega square means it's like a quadratic equation. It will have two solutions. So that's why we call it pole pair. So this second term will be summation m going from 1 to capital M. So you'll have m pole pairs here. So from there, you can find out the relation now. So JPM is actually derivative of P with respect to time. Is a polarization field. JPM is a polarization current. So current and field are always relative as del P by del T. So del P by del T in frequency domain is j omega P. So from there you can just substitute here. P is what? P is P. You can find it from here, from this relation here. P is contribution is from here. This is your chi. This is a contribution from the free space. This contribution from the polarization field. So polarization field contribution is from here. So now you multiply with the electric field with this, you'll be getting the polarization field. So that's what we're getting here. Epsilon 0 delta epsilon m omega naught square m divided by this denominator term into electric field, you get the polarization field. So j omega term is already there because we're considering polarization current. So if you rearrange the term, this is what you're getting. So left hand side you have a term here j omega, right hand side also you have a term which is j omega. That means these are time dependent term when you take the inverse Fourier transform. First term is independent of time, second term is dependent on time, j omega, so del by del t. Third term is omega square, so del square by del t square. Last term here in the right hand side is del e by del t because we have j omega here. So this is a time domain equivalent of this frequency domain relation here after you take the inverse Fourier transform. So from there you can discretize. So we'll do it second order center finite difference approximation. That is because we have double derivative also here. Double derivative I have discussed at the beginning of the class. So you need 2 time steps to find the double derivative. So if I want to find double derivative of JPM with respect to time, then I will have JPM at n plus 1 minus 2 JPM at n plus JPM at n minus 1 divided by delta t square. So since I have JPM at n plus 1, JPM at n minus 1, so I have 2 time intervals here, consideration for the double differentiation. So here also I'll use second order centered finite difference. So here instead of just doing JPM n plus 1 minus JPM n, I will do it JPM n plus 1 minus JPM n minus 1 divided by 2 delta t. This is what it means. Here also I'll do EM at n plus 1 minus EM at n minus 1 by 2 delta t, just to make sure that this relation and these relations are, comparable for analysis. So if you want to find JPM at n plus half, you just find out JPM at n plus 1 plus JPM at n divided by 2. So from the previous relation, you can find out what is JPM at n plus half. And here we have started using new notations A1M, A2M, and A3M. A1M is this, A2M is this, A3M is this. These are material dependent parameters. So finally, if you want to find JPM at n plus 1, you need to know what is this constant A1M JPM at n plus A2M JPM at n minus 1 plus A3M, then EM at n plus 1 minus EM at n minus 1 divided by 2 delta. Equation here, curl over is equal to, this is displacement current, this is the polarization current, we have just discussed it now. You can write the update equation for En at n plus 1 as C1 at En. C1 is this term here, C2 at En minus 1 this term here, C3 is this term here, then curl over it's n plus half minus half, then summation m going from 1 to capital N, 1 plus A1M JPM at n plus A2M JPM at n minus 1. So you can write the update equation now for En plus 1. So this is a procedure like last time. If I want to find En plus 1, I need to know what is En minus 1, Pn minus 1, Xn plus half. Once I have that, I can find out what is Pn plus 1. So that was about the Lorentz material. So in order to make the continuity of studying all the models, let us go to Drude model also. We have discussed the Divine model and the Lorentz model. Let us go to Drude model. In the Drude model, the electric permittivity is chi L divided by minus omega square plus j gamma d omega, and you can express this as in terms of resonant frequency as minus omega square by omega square minus j1 by tau r omega. So instead of having just one pole, if you have multiple pole here, then you have to have summation of this term here. So the epsilon is actually contribution from free space and contribution from the polarization field. So this is the contribution from the free space. So if you just add this with this here, then you should be able to get the epsilon value. So minus epsilon 0. So you just multiply by epsilon 0 this with chi, then add with this, you get the total epsilon, which is a complex value. Epsilon 0, epsilon infinity, epsilon 0. This term here is omega rm squared by omega squared g omega by tau rm. Summation m going from 1 to capital M because we have multiple pole here. So this is the Drude model we have here. So similarly, you can find out JPM is basically J omega P. So if you want to find polarization current density, is basically you do the time derivative of the polarization fields, and you have the relation. P is basically epsilon 0 chi E into electric field. So you can write down the relation we have just got now. So J omega into what is chi E. Chi is this, you multiply by epsilon 0, this is what we have here. Epsilon 0 omega rm squared by omega squared minus j omega by tau rm minus sign, with a minus sign. Then you multiply by electric field, you get the P. So then you transfer this term to the left hand side. Finally, what you get is omega squared JPM minus j omega by tau rm JPM equal to minus j omega epsilon 0 omega rm square E. So the first term, you can further simplify it. So it turns out to be this term here, you can write as first term minus j omega JPM minus 1 by tau rm JPM. And right hand side, you can write epsilon 0 omega rm square electric field. So you can write the time domain version of this frequency domain relation of JPM and electric field. So in the time domain, all the j omega terms will be replaced by del by del t. All the omega square term will be replaced by del square by del t square, but omega square term doesn't exist here. So finally, what you have is del by del t of JPM plus 1 by tau rm JPM is equal to epsilon 0 omega rm square electric field. You can write the update equation now. So update equation, you do the time discretization of del by del t. So JPM at n plus 1 minus JPM at n divided by delta t plus 1 by tau rm. JPM at n plus 1 plus JPM at n divided by 2 is equal to epsilon 0 omega rm square. Electric field at n plus 1 plus electric field at n divided by 2. So finally, if you want to write JPM at n plus 1, it will be alpha m JPM at n plus beta m. En plus 1 plus En divided by 2. So where alpha m beta m, you can find out it's this time dependent and material dependent parameters here. Finally, JPM at n plus half you want to find, you just take average of JPM at n plus 1 and JPM at n divided it by 2. You can find it out from this relation here. So the final update equation for the electric field would be En plus 1, this constant En, then this constant, then curl of H at n plus half times 10 minus half summation m going from 1 to capital M, 1 plus alpha m, JPM n. So these relations are very similar, all the models, except that there's some change in the parameters, this constant terms. Okay, so that's all for this finite difference time domain method. And these are the references I have used. Basically, there is a very good book on computational electromagnetics. This is a very old book, somewhere published somewhere in 2013, not very old. It's an old book, but they have a new edition somewhere in 2013. So I actually find this book is the best book for computational electromagnetics. These are a group of people from Sweden. They are a very famous group. I think one of the author is already deceased by now, very old person. He has contributed a lot in this computational electromagnetics. And they have a new version somewhere, probably by Springer somewhere in 2013. This is a very thin book, so number of pages is very less, and even the book size is very small. So if you want to have complete mastery over the computational electromagnetics, then this is the best book I would suggest. It doesn't go into too much details, but it has all the fundamentals on the computational electromagnetics. And the second book is actually one of the very famous book in this area. Obviously, those books which are published by Willy IEEE Press, no? These are actually the classic books. The author is James Jin. He's a very well-known personality in the electromagnetics area. He's a professor, distinguished professor in the University of Illinois at Urbana-Champaign. And this is very detailed book. So you have a very, not very thick, but little bit thick book, and you'll get almost everything about the computational electrons. You will also get idea about the electromagnetic field theory also. This is, I think, very well written book published by Willy IEEE Press. So it's a classic book on the EM theory as well as the computational electromagnetics. It has discussed EM theory as well as the computational electromagnetics. It has discussed mostly the advanced EM theory. So this is a very good book. This third book by he was a former professor at the Stanford University, Professor Inant and Robert Marshall. This is published by Cambridge University Press in 2011. Numerical Electromagnetics, the Fdtd method. This is actually a very good book on the Fdtd, and it has covered the latest topic on the Fdtd, like your unconditional Fdtd, this Fdtd for dispersive materials. Many of the previous books doesn't cover all this about the latest development in the Fdtd, like unconditional Fdtd and Fdtd for dispersive material. So if you want to learn Fdtd in great detail, this is the best book. And this last book by Stephen Gedney, I think he's a professor in the University of Kentucky. He was actually a student of Professor Rasmussen. He actually have an introduction to Fdtd method. So he is also one of the original contributor in the Fdtd field. And he has written a very thin book which will give you an introduction to the Fdtd method along with the latest development you have on the PML layer. PML, different kind of PMLs. So he has written it in a very easy to understand form. And usually Morgan and Claypool books are usually written in a very narrative style, very easy to follow. So tutorial kind of way of writing the book. So if you are interested in learning Fdtd from a pioneer in this area and who has written it in a tutorial type of explanation, you can always refer to this. Okay, so I'll end here.